Hello, I'm Mr. Adult, your favorite teacher. I'm building a website for mechanical engineering students like you to learn the core subjects in the field, since your professors do such a great job for the price you pay at college and university. The video lectures for this course will be free, but practice problems and tests will also be available in the paid course at my website, meche.education, shown below. Welcome to Statics. Today I will be introducing vectors. I hate math that isn't related to anything tangible in the real world as much as you probably do, but bear with me and pay attention for these first few videos because nearly everything we do in this class involves vectors, whether that's forces or moments or otherwise, so I wanted to create separate videos for each of the vector operations for easy reference later in this course. In physics and engineering, we use two kinds of values. These are vectors and scalars. Vectors are any value whose magnitude and direction both matter. Scalars, on the other hand, are values whose direction does not matter. Scalars can have a positive or negative value. Vectors can be positive and negative too, but it's a little more complicated and we'll go over it in depth in the next video. Some examples of values that are vectors include position, velocity, acceleration, force, and torque, or otherwise called moments. Each of these values' direction matters just as much as its size or magnitude. Some examples of scalars are mass, temperature, speed, and energy. These values do not carry any directional information, and we instead only care about their value, whether it's positive or negative. Vectors come in two forms, the first of which is an IJK form. These three letters can be used to divide the vector into its three pieces, x, y, and z. Think of it like directions. It says to go the I piece number of steps in the x direction, then turn and take the j piece number of steps in the y direction, and finally, turn and take the k piece number of steps in the z direction. Once you've taken all the steps, you've arrived at the vector. This is a simple way for us to represent the vector in our familiar coordinates. For 2D vectors, only I and j are used, since we ignore z for 2D and thus don't need k. The second vector form defines the vector using a magnitude and associated angles. Only one angle is used for 2D, but three angles are used for 3D. Here we will be deriving the equations to convert between the two forms in 2 dimensions. Our four variables are the angle defining the direction of the vector, represented by theta in this case, the magnitude of the vector, represented by m, the x or I component, and the y or j component. This is how you will typically see the ij form written out, with x being the magnitude of the x component and y being the magnitude of the y component. On the other hand, this is how you will typically see the magnitude and angle form written out for 2D. This is also referred to as polar coordinates in the 2D case. To find m, we simply use the Pythagorean theorem. From this, we can see that m squared equals x squared plus y squared, which, when we take the square root of both sides, leaves us with m equal to the square root of x squared plus y squared. We can also see that the tangent of the angle, opposite over adjacent, leaves us with y divided by x. If we take the arctangent or inverse tangent of both sides, we see that the angle is equal to the inverse tangent of y divided by x. We will derive the x and y values from the magnitude and angle by using sine and cosine. When we take the sine, or opposite over hypotenuse, of the angle, we see that the sine is equal to y divided by m. When rearranged, we can multiply by m on both sides, and see that y equals m times the sine of theta. If we do the same thing but with cosine or adjacent over hypotenuse, we can see that x equals m times the cosine of theta. These are the four equations we need to convert back and forth between the 2D vector forms. 3D is where things get more challenging. 2D probably looked familiar from sections on polar coordinates in pre-calculus and calculus, but 3D is something you probably haven't worked with up to this point. 3D vectors are a large portion of this class, so it is important to understand them thoroughly. These vectors can be given in two forms. The first form is IJK form, which functions very similarly to 2D vectors, but with a k term involved to incorporate the z dimension. The second form is the magnitude and angles form. There isn't a fancy way to write this form as far as I know. Instead, 4 values will be given for the magnitude and each of the angles, including alpha, beta, and gamma. These angles are between the vector and the x, y, and z axes respectively. These angles look scary at first, and you might be confused why it's defined this way, but the equations to deal with them are very straightforward, and I can assure you that somebody thought this one out and defined them so that the math is as simple as possible. To find the x, y, and z values, we simply use the magnitude times the cosine of the respective angle. The reason for this takes some 3D graphics to show clearly, so we're going to switch gears briefly to a 3D plot I created in Python. Basically, if we rotate this vector around in 3D space, we can make a few triangles. I'm only going to do one of the 3 triangles to show you how it's done, but all 3 can be made with the same process. We will derive the x equal to m times cosine of alpha equation. We start with our vector drawn in 3D space, then rotate it so we are perpendicular to the plane on which our vector and the x-axis lie. Now we can add our labels back onto the plot and draw another line to form a triangle. I hope this graphic was helpful, and now we can return back to our written equations. It's easy to see in this rotated view that the cosine of alpha is equal to x divided by m. When we multiply by m on both sides, we see that x is equal to m times the cosine of alpha. The y and z equations are very similar, with y equal to m times the cosine of beta and z equal to m times the cosine of gamma. These 3 equations are all we need to go from the magnitude and angles form to ijk. Let me just grab these equations real quick and bring them along because we're not quite done with them yet. If we want to go in reverse, that is from ijk to the magnitude and angles form, we can solve for each of the angles by simply rearranging the formulas to find x, y, and z. We do this by dividing each by m, then taking the inverse cosine of both sides. This leaves us with alpha, beta, and gamma being equal to the arc cosine or inverse cosine of their respective piece of the ijk form divided by the magnitude. To find the magnitude using the ijk vector, we again use the Pythagorean theorem. If you haven't seen the 3D variant of the Pythagorean theorem, it is very similar to the 2D variant. Simply the hypotenuse squared is equal to the sum of the squares of each of the sides, or a squared plus b squared plus c squared equals d squared. When we plug our values in, we see that x squared plus y squared plus z squared equals m squared. If we take the square root of both sides, it leaves us with the equation m equal to the square root of x squared plus y squared plus z squared. With these 7 equations, we can convert between the 2 forms in 3D space. That's all I have for today, so thanks for watching. If you found this video helpful, please like and subscribe and tell your classmates. If you want more resources, visit my website, mece.education. Until next time, Mr. Adult out.